Oh. So where were we last time? Where did we stop last time?
Commutation relationship between X alpha and X beta.
Sorry, repeat it again?
Commutators between X alpha and X beta.
Okay, good. Okay, let's see. Yeah, so let me just, so once again, so let's look at the, so we had that picture, right? That picture was something like this here. Okay, I used the, I was plotting the H1 eigenvalues, and here we are plotting the, I think what we're calling, so this was lambda 3, and this is lambda 8 eigenvalue. It is just a matter of choice. Okay. So because in this, if you plot like this, it becomes some very nice patterns. So okay, so so this was 2, right? So this unit, I think the units also, let's keep track of the units. So let's say this is 1, so here it's 2, right? So this was what was alpha 1. Then you have this alpha 2, which was at 120 degrees. Okay, hard to say that it's 120 or not. But the important point was that if you look at the projection here, this was -1, right? Because the eigenvalue was -1 comma root 3 or something like that, right? So this was like root 3. So, but important, this is important to remember, -1. And this angle was 120. Okay, there was a -2. So this is minus alpha 1, that is alpha 2. And of course, you continue the straight line there. And this will be minus alpha 2. Once again, its projection on the thing is 1. Huh? Because it's exactly the opposite. So if this is -1, that should be +1, right? And then finally, alpha 3 was 60 degrees. 60 degrees, whose again, the projection here was +1, okay. And like that here. Alpha 3 and minus alpha 3. Okay. Now we already have the, so what are the commutation relations? So we have commutation relations between kata and karta, which is of course 0, because by definition kata and sub, yeah.
You should start recording.
I recorded, I think I started, yeah. Now it's become my habit. The moment I enter here, turn it on. Yeah. Okay. Then the commutation between C and the various non-zero roots. So X, alpha 1, alpha 2, alpha 3, etc. But this we already know. This is simply given by, so if I take an H, where H is an arbitrary element of the Cartan subalgebra, then this is simply given by alpha, whatever alpha is. So generally, let me just call it alpha H, X alpha. And this alpha could be one of those 6 alphas. Now we need to also find out what is the commutation relation between. So this is the commutation relation between C and the rest. This gives you that. But then I have to also look at the commutation relation between the rest of that is X's and the X's. Okay. So this is what we're going to do. Now, X alpha with X minus alpha. So what did we do? How did we proceed? So the main concept here was that whatever it is, if I choose, for example, some X alpha and X beta commutator, this must be some state in the original Lie algebra, but must be an eigenstate under the action of add H. So add H acting on this guy will give you again some number times this guy, right? And the way we did was simply to use so add H acting on this. This is an important thing. I'm repeating it because this is an important thing. Okay, so if it acts on this, then by Jacobi identity, this is the same as H, X alpha, X beta. And then by Jacobi identity, this is same as H acting on X alpha, X beta, plus X alpha, and then H acting on X beta. So that is what I mentioned to you, that this behaves like a derivative using the Leibniz rule. Jacobi identity is just that statement. But then this implies, since this is an eigenstate, so this is equal to alpha H times X alpha, and then you get X alpha X beta commutator. And here also you get, this is the beta H times X beta. So once again you get the same commutator again. Because alpha H and these are numbers. So you can pull that out of the commutator. Right? So you'll get here alpha H plus beta H times the original value. Yeah. So what we are seeing is that, I mean, after all, this is nothing else but alpha plus beta H. So we are seeing that, so this state is, of course, this is an eigenstate. And in fact, the eigenvalue is simply the sum of these two eigenvalues. Right? So it's a sum of that. So there is a nice structure here. So we see that if I take alpha 1, alpha 2 commutator, well, first of all, let's see alpha 1 with minus alpha 1 commutator. What will I get? Answer must be 0, right? Because beta is minus alpha, so it becomes 0. But 0 means that this must be in the Cartan subalgebra, right? Because it should commute with all the Cartan. So that means we say that X alpha with X minus alpha belongs to C. Of course, we can determine exactly which one, right? So for example, X alpha 1 with X minus alpha 1 will give me H1, some number times H1, maybe 2 times H1 or something, right? Because that was because remember, these were all upper block, non-zero, this was just sigma matrices in the upper block, upper 2 by 2 block, right? Similarly, if you take alpha 2 minus alpha 2 and that particular combination, which, I mean, some lambda 3 minus root 3 lambda 8, minus or plus, I'm not sure, one combination, which brings this object, this makes it exactly 0, 1, minus 1, and 0, 0, 0. Right? That particular combination with the sign, you can determine what that sign is. Then this would be alpha 2, and alpha 2's were what? Alpha 2 was, here it was 1 and everything else was 0, and minus alpha 2 was 1 was here and everything 0, right? So this is like, you take this 2 by 2 block, this would be like the sigma 3, right? And the other two, alpha 2 and minus alpha 2 are simply sigma plus and sigma minus, right? So clearly the commutator of these two will give me back some number times this, right? So this part is fine. And if you look at the commutator of this with that, you will get again some combination. It will be some element of the Cartan subalgebra. I mean, it will be something which will form an SU2 subalgebra here. So how does it work? X alpha 3 was 0, 0, 1, everything else 0. And X minus alpha 3 was 0, 0, 0, 0, 0, 0, 1, 0, 0. So the commutator of these two will give me something which will be in the Cartan, and it will be of the form 1, 0, minus 1, and everything else 0. Yeah? Which will be some combination of, again, lambda 3 and lambda 8. Okay? So you can precisely find what combinations appear. But the upshot is that this is going to be in the Lie algebra. Right? One thing which is important is that this is not 0. I mean, after all, 0 is also in the Cartan subalgebra. Cartan is a subalgebra as a vector space. So 0 is also. But the point is that it is not 0, which we see explicitly here for all of them. Now, when we discuss the general theory, we see that it's a general feature. It's not just for SU3, it's a general feature. For the class of algebras we will be studying, this is always the case. The class is semi-simple, which I have not defined yet, but we will define all that later when we discuss more generally. So for this class, there's always the case that it is not 0. Okay. The fact that it is not 0, it implies that you have an SU2 subalgebra. For every non-zero root, there's an SU2 subalgebra. You see, why? Because let's suppose it's not 0, so let us say it is something, some particular h belonging to C. Okay, it will be some h, some element in the Cartan subalgebra, non-zero. Important point is non-zero. Then you see I can immediately form an SU2 subalgebra, because if I take this h and look at the commutation relation, this will be alpha h x alpha, and h x minus alpha gives you minus alpha h x minus alpha, right? So you see these three generators have formed a subalgebra, and that's exactly the SU2 subalgebra, right? SU2 is the basis of sigma plus and sigma minus. These are like behaving like sigma plus and sigma minus. So that is very important to see. So therefore what we are seeing is that for every non-zero root, there is an SU2 subalgebra which consists of this, and a particular element in the Cartan. I mean, I put here, you see, this is zero root, right? So what is a zero root? They correspond to the Cartan subalgebra itself, because Cartan subalgebra commutes, right? So you can think of it as eigenvalue 0. So this thing forms an SU2 subalgebra. Similarly, this forms another SU2 subalgebra, okay, and this forms another SU2 subalgebra. Now that is very important because let me continue here. So this was only x alpha x minus alpha, right? But what happens if I look at, for example, this is alpha beta, but beta is not equal to minus alpha. So let's look at this guy here, where beta is not equal to minus alpha. So these are such that alpha plus beta is not 0. In that case, there are two possibilities. It could be, I know whatever it is, it must have eigenvalue alpha plus beta. I mean, the root must be alpha plus beta, right? That we saw that previous argument. We saw that this will be again an eigenstate with respect to the adjoint action of the Cartan subalgebra, and precisely also we determined that eigenvalues are simply alpha plus beta. But it might happen that in your root space there is no alpha plus beta, right? For example, if I take alpha equal to alpha 1 and beta equal to alpha 3, if you add that up, you will get something here. But this was not a root, right? So there is no such element in your Lie algebra to begin with, the full Lie algebra to begin with. So in that case, it will be 0. So the conclusion is it will be 0 if alpha plus beta is not a root of the full Lie algebra. Now, if it is a root, then it will be proportional to x alpha plus beta, right? Some proportionality constant, right? But could it be 0? That's a question. Okay? Could it be 0? Now that depends. I mean, now at least in this SU3, we see that. So what is the possibility? If I take alpha equal to alpha 1 and beta equal to alpha 2, in this case, the sum of these two is actually alpha 3, right? So x alpha 3 exists. But now the question we are asking is that could it be that this coefficient happens to be 0? That's what we are. Now that is where these SU2 subalgebras are playing an important role. These SU2 subalgebras. Look at this SU2 subalgebra. Okay, and now look at this state. I mean, forget everything else. We are just focusing on this SU2 subalgebra. See, everything has to fall under this SU2 subalgebra, right? Some representation of SU2 subalgebra, right? And we know for SU2 subalgebra, our SU2 algebra, we know all the representations, all the finite dimensional representations. We know the spin J representations, right? And we know what are the eigenvalues in that spin J representation. Now, if you look at this alpha 2, this one, so let's say this was I think what we were calling lambda 3. So remember x alpha 1, x minus alpha 1, and lambda 3, which is what we were calling H1. This formed an SU2 subalgebra. Right? Because the commutator of these two will give you something times H1, 2 times H1. So this forms a subalgebra. So now if I look at the eigenvalue with respect to H1, that is what we have the n quantum number in the SU2 representations, right? the J and M. J would be the highest possible value, and M would be any quantum number in that representation, right? So what we're saying here is that if a H1 eigenvalue gives you the M quantum number of this SU2 subalgebra, right? Now here, if you look at this one here, you see this -1 is the M quantum number. Actually, it is not, because I mean, there's a factor of 2 with respect to the previous normalization, because here we were just taking sigma 3 to be the H, no? Whereas previously we were taking sigma 3 by 2. So what we will have is 2 times M here. So this number will be 2 times M, right? So this is certainly not a singlet representation, right? It is some negative value. That means if I apply the raising operator, this is the raising operator, that's the lowering operator of this SU2, right? And this is the kappa. So this eigenvalue is M, minus 1, which in our normalization is minus half. I mean, the previous normalization would be minus half, because previously we were taking sigma 3 by 2, no? So you divide these numbers by 2 to compare it with the spins. So it's a minus half. That means whatever this representation is, it must have first of all a half integer j, right? And the j must be at least greater than or equal to half, right? It must be at least equal, because we have an M quantum number, right? It could be greater, of course. It could be j equal to 3 half or 5 half, could be whatever, right? We don't know that yet. But if so, then this state, if I apply a raising operator, it cannot be annihilated, right? Because it should give me something with a plus half. But this is exactly the commutator we are talking about. So when we look at the commutator x alpha 1 with x alpha 2, okay, this is nothing else but add x alpha 1 acting on x alpha 2. Okay, there's some representation of this. This should fall in some representation of this SU2. This SU2. Right? So therefore, this cannot be 0. What we are saying, it should give me some non-zero number times a state which has eigenvalue plus half, times something here, let's say y, which has eigenvalue plus half with respect to this h, not h by 2, h1 by 2. But which is a state? Of course, we already knew that if the commutator of this must be proportional to that, right? The only question is whether the coefficient is 0 or not, right? But what this argument is saying, coefficient cannot be 0. You see, and indeed, you see, this is exactly a plus 1 here. So this was minus half, and that is plus half. And that's it, it stops. Because if I apply another raising operator, I mean x alpha 1 again acting on that, it gives you 0. That means this is the highest weight state with respect to this SU2 subalgebra. So this means these two things together forms a spin half representation of this SU2 subalgebra. Okay. Similarly, these two will form again a spin half representation with respect to this SU2 subalgebra. So this proves that this cannot be 0. I mean, this coefficient cannot be 0. So we knew that this is going to be some number times x alpha 3 already, but what this is proving is that this coefficient is not 0. So that is why this structure is so tight. You see, I mean, this hexagon that we are finding, because you see, this was for this SU2, but we have several SU2s. Now look at this SU2. Okay. With respect to that, these two guys will form a doublet. Okay. And these two guys will form another doublet. Or take this SU2. With respect to this, these two will form a doublet, and these two will form a doublet. So it's a very, very tight structure. No? That is the reason why we are getting such beautiful geometric pictures. And this is going to be there for all the algebras, all simple algebras. We'll have this situation.
So you can always find a SU2 subalgebra for any SUN?
Yeah, correct.
And is that also similar for all the other semi-simple?
All of them, SON, SPN, all of them. Or even exception, there's some exceptional algebras. E, E6, E7, E8 and so on, all of them. Because this is the general statement. For every non-zero root,
Yeah.
you see, what is the argument? We first find the Karta subalgebra. Then we look at all the rest of the guys and find eigenstates with respect to this, right? But what this statement is saying is that once I find a non-zero root, then that non-zero root gives rise to a 1SU2 subalgebra. Because this is the statement. Alpha with minus alpha will be some h. And these three things, these three generators form an SU2 subalgebra. Okay. So it's a very powerful statement here. Right? So every non-zero root corresponds to 1SU2 subalgebra. Of course, this and this guy both will correspond to the same SU2 subalgebra. And similarly, positive and negative root. The corresponding negative root will be part of the raising and lowering operator of that SU2 subalgebra. So, yeah, this is the general pattern. So our strategy will be this, to look at these different SU2 subalgebras, and okay, this particular thing was just a joint representation, right? But you can do it for any representation now, you see. Any irreducible representation can be obtained by just taking a highest weight state of this SU2 and that SU2. No? You take some spin J1 with respect to this, spin J2 with respect to that, and that will just give you a irreducible representation. Okay. By successively applying the lowering operators, no? You will get that. Yeah, so that was the, let me see what else I have to say here. Was there anything else I have to say about this here? Any question? Let's see. Is there anything else I have to say? If not, then I will move to the what is called the defining representation, fundamental representation, and again look at all the possible eigenvalues. But was there any else? Any questions here? Because it's important to understand this here. Maybe I can just mention something. Yeah, okay, let me just mention one thing, which we'll discuss in much more detail when we go to the general structure, generally algebras. You see here, we had, I mean, for a given SU2, for the SU2 case, we had, okay, we said one of them is a raising operator, other is lowering operator, right? But now when you have different SU2s, it becomes a little difficult, right? I mean, should I call, I call this guy raising operator, should I call this guy raising operator of this SU2? Or should I call this guy raising operator of that SU2? Because there is not particular sense in, I mean, positive or negative, it doesn't matter. It's various directions, we have various directions in two-dimensional space, right? This is not two-dimensional. This dimensionality is the same as the dimension of the Cartan subalgebra, right? So, for example, if you go to SU4, this will be in 3 dimensions. Right? So, what is the meaning of, you say, you have to choose some convention. Basically, that's what I'm saying. If you choose some convention, to say, okay, this is positive, this is raising, and that's lowering. No. For that, what you do, of course, choice is completely, it's not important. No. But nevertheless, you have to choose something. And the way one chooses this is, you will just draw arbitrarily. So there are too many lines here now. There are too many lines here. It's hard to see anything here. So once again, close this here, and this here, this here. Yeah, so this was the alpha 1. I mean, these are all projecting to -1, so we have +1 and -1. So what you do is, so we were calling alpha 1, alpha 2, alpha 3, minus alpha 1, minus alpha 3, minus alpha 2. Okay, and what you do is you just choose some hypersurface. Okay, in two-dimensional case, it will be one-dimensional line. In a SU4 case, this will be 3-dimensional, right? So what you need to do is to draw a 2-dimensional plane, which bisects the space into 2 parts, right? You want to divide this space into 2 parts. So this you do by, in this case it's just simple. You just take any line which passes through the center, through the origin, but the important point is this line should not be overlapping one of the roots, which is of course possible because actually there are infinite number of ways of doing it, right? But you pick your own favorite line that you choose, right? And declare that all the roots on the one side of this line are, say, positive, like raising operators, positive, and all the guys on the other side are lowering operators, right? Or negative roots. So in this language, we just, instead of calling raising and lowering, we just use the word positive roots and negative roots. That's what they do. So in this way of thinking, if I draw this line here, then alpha 1, alpha 2, alpha 3 are positive roots, and all the other guys are negative roots. That's why. If somebody had chosen this line, for example, then alpha 3, alpha 1, and minus alpha 2 would be the positive roots. And okay, so let's say I choose this one. So I have so one side of it. So positive roots in that case will be alpha 1, alpha 2, and alpha 3. Okay, for that choice, for this choice here. Now, here again a curious fact you can see that in this positive roots, I can choose if I just stay within the set of positive roots. The property here you see is alpha 1 plus alpha 2 was equal to alpha 3, right? On the other hand, alpha 1 plus minus alpha 3 is equal to minus alpha 2, right? Things like that. In other words, or another way to say is that if I want to get alpha 2 from alpha 1, you need to, the important point is that these coefficients, what I am writing here, coefficients are positive, non-negative, you see. Yeah. I could get alpha 2 from the combination of alpha 1 and alpha 3. After all, it is 2-dimensional space, right? So I should be able to get some combination of alpha 1, alpha 3 as alpha 2 as that, right? I can write alpha 2. So for example, I can write alpha 2 is equal to, this is same equation, minus alpha 1 minus alpha 3, right? So then you would say, okay, I might equally well choose alpha 1 and alpha 3 as a basis.
Plus alpha 3.
Right? Huh? Maybe I made a mistake. Alpha 3. So plus alpha 3, sorry. Plus alpha 3 minus alpha 1. Correct. Okay. So I could have, the nice thing about this choice, alpha 1 and alpha 2, is that the remaining positive root can be expressed as linear combination of alpha 1 and alpha 2 with non-negative coefficients. Okay? Non-negative coefficients. Whereas if I had there's just it will become clear later, but that such choice these are called simple roots. Simple roots. So alpha 1 and alpha 2 are called simple roots. Okay, this is a definition, which will become again clearer later. What is the importance of that? Because in SU3 you don't need, we have everything explicit. No? So the important point is that there exists always a set of simple roots in any Lie algebra, such that every positive root can be expressed as linear combination of simple roots with non-negative coefficients. Actually, even integers. It turns out it has to be integers also. Okay. So at any rate, non-negative. Whereas, if I had chosen alpha 1 and alpha 3, you see, you couldn't write alpha 2 as a combination of these two with non-negative coefficients because this is negative, right? Now, it is a fact that the number of simple roots is exactly equal to the dimension of the Cartesian algebra. It's a kind of non-trivial fact, no? That you can choose like this. So, okay, it turns out that that's the case. So you choose this simple. So this is my simple roots. So with respect to this, what happens? Everything kind of neatly splits. all the positive roots can be expressed as a linear combination of these two with non-negative coefficients, and all the negative roots can be expressed as a linear combination of these two with completely negative coefficients. I mean, no positive coefficient there, right? Because minus alpha 1 is simply minus 1 times alpha 1. Minus alpha 2 is minus 1 times alpha 2. And alpha 3, which is alpha 1 plus alpha 2. So minus alpha 3 is minus alpha 1 minus alpha 2. So you see, the positive and negative roots split in a nice way, where one side is obtained as non-negative coefficients with a combination of simple roots, and other side is completely obtained by combinations of these two but with negative coefficients, non-positive coefficients. There's a clear split.
And the coefficients are determined from the normalization that is used for the Kleman matrices, right?
No. This is totally independent. I mean, this is totally independent of any choice of basis.
What?
Yeah. I mean, this has nothing to do with the basis. This is a statement for every h, you see. So what this is a vector of the dual vector space. So we are saying that alpha h plus beta h, irrespective of the choice of the basis. This is simply by linearity. Yeah?
That's it.
Yeah.
Sorry.
I mean, it's just that for this choice, there are some nice pictures up here. I mean, just imagine if I had chosen to plot h1 and h2 eigenvalues, then the picture would be somewhat different. I mean, it would be, I don't know, let's see. This alpha 2 root would have been just here, and this would have been here, and alpha 3 root would have been somewhere here. Yeah, because, I mean, it's a matter of choosing your basis, right? I mean, eigenvalue of the alpha 2, or no, maybe not. Anyway, it won't be this. It will be kind of distorted. In fact, what was it? I mean, do you remember the coefficient? We can read off from that coefficient which we had obtained a few days back or yesterday. Yeah, it was written here, right? So if you look at the numbers here, alpha 1 of AH1 plus BH2 was 2A minus B. Alpha 2 of AH1 plus BH2 was minus A plus 2B, and finally alpha 3 of the same thing was equal to A plus B, right? So now we want to plot the eigenvalues with respect to H1 and H2. So the alpha 1 is has the eigenvalue 2n minus 1. So okay, this is not the right picture. So if I plot H1 and H2 eigenvalues, then for alpha 1 the eigenvalue here was 2, right? I mean this part, but with respect to H2 it was minus 1. So this point will be actually somewhere sitting down. No? It will be somewhere here, 2 units and minus 1 unit. So this will be alpha 1. No? Here it will be alpha 2 will be minus 1, so it comes here minus 1 and minus 1 and then 2 units up plus 2. So it will be something like this here. And finally this one is A plus, maybe the picture is not right. 2A minus B. Anyway, the third one is coming like A plus B, so 1, 1. So it is somewhere here. And then the negative roots. So it will look kind of pulled out hexagon here. Okay? I mean, it's not a regular hexagon. That is just because we are not normalized in a convenient way. You know, that is all. I mean, they're not orthogonal. I mean, the trace is not 0. Trace of H1 times H2 is not 0. So for this reason, it's a bit distorted. But that is not very important. As far as even here, you see this. If you just add these two vectors, even in this basis, if I add alpha 1 and alpha 2, I will get alpha 3. It's not. That's independent of this choice of normalizations. Yeah. Right. So once you have defined this set of positive simple roots, it is enough to just specify the highest weight with respect to this SU2 subalgebra and the highest weight with respect to this subalgebra. So this J quantum number, so J1 and J2, these two guys, determines the irreducible representation uniquely. That is the idea here. So let us now try to look at some of the simple representations, and then we also discuss the tensor product of these representations. So let's look at the simplest possible fundamental representation, okay, which is a defining representation.
Then the coefficient depends on the basis that we choose.
Which coefficient?
For example, for obtaining alpha 3 in terms of alpha 1 and alpha 2.
No, it will be exactly that. Yeah. I mean, because eigenvalues are additive. Eigenvalues are plainly additive, right? I mean, you see that alpha plus beta, I mean, it's purely additive. So it's not, it's just a pure vector sum. So if this is alpha 1 and that is alpha 2, just add these two vectors and then you will get alpha 3.
Yep.
Yeah. That's because you can add here, see, already. You can just add the two, that's what gives you 1, 1.
Oh, yes. Okay.
Yeah, this is, okay, since you brought up this issue, this is one thing. Let's say this. Yeah, I'd say another curious feature that you notice here is that the sum of, if I take sum of all of this, I mean, this was of course, because for every positive root there was a negative root. So of course the sum is going to be 0, right? But could you have just sort of guessed it? I mean, already, and that again comes from, I mean, is it a general fact? No? Is it a general fact, for example, there are several issues here. Is it a general fact that for a given alpha there is also a minus alpha root? No. There are several questions you might ask, right? As I said, SU3 we saw explicitly just by working on the commutation relation. But in general, when if you take big Lie algebras, I mean SUN for large n, it will be very difficult to really work out everything, right? You can imagine 3 by 3 matrix already is a difficult thing. So, so can you, for example, ask the question, say that for if alpha exists, then minus alpha must also exist as an eigenfunction, a root as a root, right? But suppose even if I didn't know that, so what happens is that basically you take the trace of add of h, of any element h. You remember how we proved in SU2 case. In SU2 case we proved that, that you remember how we wrote it? We said trace of sigma 3 or sigma 3 by 2. H, let's say H is eigen. That was the same because I could obtain H as a commutator of J plus and J minus, right? With some coefficient, 1/2 or whatever, some number, right? So, but some non-zero number. H I could write it as commutator of J plus and J minus. And then a trace of this commutator must vanish. That was the idea, right? So from this you can prove that if I take the eigenvalues of a given H and trace it over all the full representation, it must be 0, right? And that is true for any H. Okay. In the SU2 case there was only one H, I mean it was one dimensional. In SU3 case it's 2 dimensional. So both the H1, H2 or any combination of H1 and H2, they'll be traceless in any representation. Okay. And that is because these eigenvalues are these guys. So what we are saying is that the sum of all of these must be 0. Okay. This still doesn't tell you that for every alpha there should be minus alpha. Okay. But it does tell you that the sum of all these vectors, root vectors, must vanish. So there are a lot of nice things that you already start seeing in this example of SU3. There are a lot of non-trivial features here happening, okay, which will become clearer when we go to the general discussion. But here at the moment is observation.
Can you show that the trace over a single SU2 subalgebra becomes 0?
Trace over? Trace over?
On a single SU2 subalgebra.
Yeah.
If we can show that, then we can say that for every alpha.
True. Yeah. But the point is that even the existence of SU2 depends on the fact that for every alpha there is a minus alpha.
Okay, so it's other way around.
Yeah, it's the other way around. So in order to show that SU2 algebra, subalgebra exists, you need to prove that for every alpha there should be minus alpha. And this will be in general not true. But for the kinds of algebras, semi-simple algebras that we'll be talking about, this will be true. Okay. For that, we need to wait a little bit. So there are some concepts, notion of a metric. You need to define a metric on the Lie algebra. Okay. Cartan killing form, right? So you have to define a Cartan killing form, and the semi-simple algebras will be the one where this Cartan killing form is non-degenerate, which means the determinant of the metric is not 0. So metric is invertible then. In those cases, you can show that, and so if the algebra is semi-simple, metric has to be non-degenerate. But then you can prove that if alpha existed and minus alpha did not exist, then you run into a contradiction. You find the metric is degenerate. Okay. Therefore, minus alpha must exist. So this is the kind of logic which will appear. We'll see later. But here it's happening automatically because SU3 is a semi-simple algebra. So it was guaranteed. I mean, but we don't see it at this stage. Okay. So now, if there are no questions on this, now let's go to the fundamental representation. Okay. Okay, fundamental representation, much easier because that was a defining representation, right? So we already know H1 we chose it to be 1 0 0 0 minus 1 0 0 0 0, and H2 we have defined it as 0 0 0 0 1 0 0 0 minus 1. Okay, now this is the fundamental representation. So I mean this is a defining representation, but which is what we call fundamental representation. Right? So clearly these are 3 by 3 matrices. So this is going to act. This will act on a 3-dimensional 3-column vector. Okay. This is going to act in some 3-dimensional space as just by matrix multiplication. Right? So I have some vector here. Let's say x1, x2, x3. Some vector. And the action of H1 would be in the fundamental, will be simply multiplying this matrix. So it will give you another 3-dimensional vector. Similarly here and this one. So we want to ask, can we find eigenfunctions with respect to both of them simultaneously? And the answer is actually pretty simple because these are diagonal matrices. You can just take each one of these elements. Eigenfunctions will be 1 0 0. 0 1 0 and 0 0 1. That's because these are diagonal matrices. So eigenfunctions are all immediate. The 3 eigenfunctions. So I don't know. Let's call it. Okay. So let's call it E1, E2, and E3. I don't know if we call the same name, but okay. I just give it a name. E1, E2, E3. And now let's look at the action of AH1 plus BH2 on E1. What will I get? So here you just get A times that, and here it is nothing because this row is 0, right? But it's a matrix multiplication. This times that, no? So multiply with that, it gives you 0. So this is simply A times E1 itself. Now if I take AH1 plus BH2 acting on E2. Well, so the relevant E2 is this one, so the relevant thing is the second row, right? Everything else will be 0 anyway. So, not second row, sorry, second column, right? Because this is going to multiply there. The only non-zero entry is that, so relevant thing is only the second column. Right? Because, so here you get a -1, so minus A, and here you get plus 1, so plus B, times E2. And finally, say AH1 plus BH2 acting on E3. Now only the third column is relevant because E3 is only non-zero element is that. So this will give you 0 and that will give you minus. So minus B, E3. So now I can again write down the weight. So this eigen, just like these eigenvalues we were calling as roots. Now, these eigenvalues are called the weights. That's the name, weights. So these are called weights of this representation, right? Or this three-dimensional representation. So we can draw a picture again. And once again, you see, you will get some distorted picture, which again, if you sort of choosing H2, if you had gone to that lambda 8, again, you will get nice pictures. But as I said, it's not important, but it's easier to remember. Okay, so if I plot this in this plot of H1, H2 eigenvalues, so the E1 is simply 1 here. So E1 gives you 1 here. So this is E1. E2, E1 was simply 1 here. E2 is -1 plus 1. Okay. So -1 means that here, so somewhere here. So this is E2. And E3 is simply -1. So E3 is coming here. E3, E2. Right? Because this is only B is not, only the second. A doesn't appear here.
Can you also do this by taking H2 and lambda 8?
So repeat again.
Can you also do this by taking H2 equal to lambda 8?
Sure. But I mean, yeah, but here I just chose this particular H2. So we can just do that. Yeah, correct. That may be easier actually. So let me just write lambda 8. Lambda 8 was 1, 1, -2, 0, 0, 1 over root 3, right? So we can ask what is eigenvalue with respect to lambda 8. So the first one is simply 1 over root 3. So eigenvalues of the E1. I just write the eigenvalues of H1, EV of H1, and eigenvalues of lambda 8. Right, like that. So this one, of course, is the same. So this is 1. But here we get 1 over root 3. Okay. For the E1. This is for the E1. For E2, we find this will be -1. Okay. E1. And here is again plus 1 over root 3 because the second column that's going to multiply. So 1 over root 3. And finally, the last one, which is this is 0, and here you get -2 over root 3. This one E3. Okay. So if I plot now in this H1 lambda 8 eigenvalues, so here you see, so you get 1 unit here, and 1 over root 3 unit here. So it's something like here. Huh? So this would be, let's say, W1, the weight. The weight. This is W. I'm just calling W. Huh? Instead of alphas, I'm just calling W. So W1 is the weight for E1 for this eigenvector. Okay. Here you just get -½ 1 over root 3. So it is here. So it's just a reflection, no? Of this here. That is W2. And W3 is so two units of that. So it's somewhere like, okay, this is not very precise, the scale. So this is -2 over root 3, this part. Okay. The length squares of all of them, if I just add the lengths, so this is 1 plus 1 over 3. So length square is 4/3, right? 4/3 here, 4/3 here, and 4/3 here. So all the lengths are the same. This length, I mean, this picture is not very precise. I've not scaled. This is not 1 over root 3. That's what I'm saying. It's a little bit different. So these lengths are all the same. And this angle is, if you see the tangent, tan of this angle is 1 over root 3. Okay. So this is 30 degrees. And that's also 30 degrees. So you see that this becomes an equilateral triangle. Okay. So that's the picture here of the fundamental. Which is, so it's the same thing here. You see this, here in this picture you have W1, W2 and W3. So it's kind of distorted. I mean, you know, this guy has moved up there. It's not a simple rotation. It's not a simple rotation because we are changing the dot. There's an inner product is not orthogonal. It's not orthogonal.
We can also make a connection with physics of this diagram that I was thinking.
Sorry, I cannot hear.
We can also make the connection with this diagram with the physics of quarks, that is hydrospin and hypercharge.
Yeah.
So can we do this with that diagram?
It's not important, right? Because after all, H2 is what? H2 is some combination of H1 and lambda 8. So it's just rewriting this in a different way, right? There is no difference in physics. Physics is the same.
Yeah, there is no loss of information.
Exactly the same information. Right, I mean, so in fact, indeed, this is lambda 8 is usually called the hypercharge. So in physics, usually we use this basis. Hypercharge, and this will be the isospin. No? Kind of, that is what the language is. Yeah. I mean, originally, Gell-Mann introduced this thing long time back. Gell-Mann. This is much before, I think this was before even QCD was known. No? It was even before the quarks were kind of postulated. No? But this was even before that, where people, of course, knew mesons. No? So what he did was he found there were various mesons were known. One was the pi meson, which were pi plus minus and 0, a neutral meson, pi meson, and a positive charge and negative charge. And then the k mesons were known. So we had a k plus minus, and then there were two types of k zeros, neutral. I mean, two types of k zero. Okay. So there are some combinations, some things were known. So what he did was, and they didn't have the same mass. Okay. They have different masses, but the mass difference was not too much. Okay. So Gell-Mann said, okay, let's, to the 0th order approximation, assume that they all have the same mass. Okay. Then perhaps there are some quantum corrections which make them different. No? But let's just to start with, assume that they are all massless. And then he said that, then he thought that maybe there is an SU3 symmetry between all of that. Okay. And basically he put there pi plus, pi 0, pi minus, and various k plus and k minus, k0, k0 bar, etc. Okay. And actually there was, in fact, he was not thinking of SU3. I mean, there should be, sorry, SU3, there should be one more, right? Because the Cartesian subspace is two-dimensional. There should be 8 of them. So there is one more, some eta or something like that. It's called another meson. He puts all that together, and so that was original motivation for it. Of course, now we don't think in terms of that. Nowadays we think in terms of quarks, because quarks have also an SU3 symmetry, right? So quarks would be sitting in this representation, fundamental representation. But when you construct mesons are bound state of quark and anti-quark, QQ bar, and they will be in their joint representation or singlet representation. So there are these all possible representations they come. So it appears in a different way now compared to what Gell-Mann initially thought of. But nevertheless, it plays a crucial role in the standard model. Okay, so this was the representation. Now you see, notice that for every in this representation, W1, there is no minus W1 in this representation, right? Unlike for the roots, for every alpha there was a minus alpha. Here it is not happening. Okay, so now again from this picture, we can see, looking at this picture, what will happen if so this just tells me the eigenvalue. So far we only looked at the action of the Cartesian subalgebra. Now we want to ask about the other generators, how the other generators will act. Well, other generators have these, what we call x alpha 1 alpha, x alpha 2, x alpha 3, etc. No? So from this picture again we can see, by comparing it with that picture, you see this eigenvalue was 1, right, here. So this object, this W1 has, if I apply the H1, I get an eigenvalue 1, which means it is, n quantum number is plus half, because we have to divide by 2. No? So it's plus half. So therefore, again, with respect to this SU2 subalgebra, this must be a spin half or some half integer spin representation, right? So in particular, since it's positive plus half, if I apply x minus alpha 1, it should take you to the minus half, which is that. Okay. When I apply x alpha plus alpha 1, this one, it will take you here because again it's additive. You know, this, the weights and roots are always additive. When I apply this here, I'm going to get something here, but it doesn't exist, which means this is the highest weight. Okay. This state is the highest weight with respect to this SU2. Okay. Let me, since I made this statement here, but I didn't prove that. Let me just prove this statement also. Yeah. Remember I told you that in the adjoint representation, now if I take the commutator of any of these two guys, the result will be again an element of the Lie algebra. It will be still again an eigenfunction, but with the eigenvalue being the sum of the two roots, right? That was because eigenvalues were additive. No? But we have not proven that. Now for the arbitrary representation, this was the adjoint we proved, right? So let's just also do that. Now what can I erase this? Maybe I can erase this part here. Okay. So now let's suppose in any representation R of some x alpha. Okay. I apply this on some R dimensional. This is a R representation. It will have some dimensionality. So it will be that dimensional column vector. Okay. In the fundamental case, this was a 3 by 3 matrices, and that was a 3 column vector. But generally, it will be some dimensional. Suppose this R is a d-dimensional representation. D-dimensional representation. Then this will be D cross D matrices, and this will be a D column vector. D column vector. Okay. Now suppose I have found some weight for this representation. So what does it mean? R of any H will be R acting on this V equal to WH V, right? So I put here subscript W to indicate that this is the eigenvector with the eigenvalue W. Just like what we did for the adjoint. Adjoint, it was add add of H acting on, we said X alpha was simply alpha H X alpha, right? That was the adjoint representation. But now we are saying this is true for any representation, right? I can just find the eigenfunctions, and for the Cartan subalgebra, because I can diagonalize simultaneously. Cartan subalgebra commute with each other, so I can diagonalize simultaneously. So I can find eigenfunctions, simultaneous eigenfunctions. And those eigenvalues I am writing as this. Because again it's a linear action, right? So there's going to be W will be again some dual vector space to the Cartan subalgebra. Okay? And you get that. Now, so now what we want to prove, so here what we prove that if I take add H and take the commutator of X alpha X beta, then this action gives you alpha plus beta H acting on the commutator X alpha X beta. Right? But this is the same as add X alpha acting on X beta. Right? So this is also add X alpha acting on X beta. So you see what's happening. The X beta is playing the role of V. I mean, after all, in the adjoint representation, this space is itself the Lie algebra. Right? So that is the analog of V. Okay? This is the analog of R. Instead of any representation, it's add adjoint. Add is a short form for adjoint. So what we are saying is that when I apply adjoint X alpha on some eigenvector X beta, then this result will be again an eigenfunction of add H, but with eigenvalue alpha plus beta. Okay? And the same thing will happen here. So let's just do this here. Let's just check that. So how will we prove that? So we want to claim that if I apply this on the VW, so we want to prove that X alpha VW is again an eigenvector with eigenvalue alpha plus WH. So so that's what we want to prove. Let's see. So, okay. So remember this equation is satisfied. Okay. And now I want to ask what happens if I apply RH on this. That's the question, right? So again, the trick is always this. The only thing we know about algebra is the commutation relation, right? So we just try to use a commutation relation. So we write this as the commutator RH, Rx alpha, acting on VW, plus I have to of course add the other part, right? Because in order to write it like this, I have to subtract minus Rx alpha RH, and then I have to add that also. So plus Rx alpha RH, acting on VW. Right? Now this commutator is in fact alpha H Rx alpha, because I mean because I used here the definition of the representation. Representation satisfies this condition that this is nothing else. So the first term is the same as R of the commutator of H with X alpha. Right? That is one of the conditions representation has to satisfy. Correct? That's acting on VW. And the second one, RH acting on VW is simply WH. This is WH times VW. WH is a number, I can take it out. Okay. So the second term is WH, Rx alpha, VW. Okay. Now use the fact that this guy is nothing else but alpha H times X alpha. Okay. Alpha H is a number, and the representation is always linear representation, right? So I can take this out. So you get alpha H times Rx alpha acting on that. So the first term is simply alpha H acting on Rx alpha, VW. So you see this is just added up. So it's alpha plus W acting on H times R. So they add. So it's just take these vectors. So whichever one you choose one basis. Either you choose this basis or that basis, but then you should not change it. You have to use both for the representation and the adjoint. You have to use both the same diagram. So if you use this diagram here, then I have to use this diagram here, and then you see immediately that when I apply X alpha, so I have to unfortunately draw in the same picture. I have to draw both. So I don't know how to draw this. So the picture would be, notice that this is 2 units, right? This was a 2 plus 2, and here is 1 unit. So alpha will come up to here. Alpha 1 will be somewhere here, and alpha 2 will be this is 30 degrees. Alpha 2 was somewhere here. Okay, with its projection was again 1 minus 1. So it is just vertically above that alpha 2. And alpha 3 is the sum of the two, somewhere here. So if I apply X alpha 1, X alpha 1 on this vector, I'm going to get a weight vector here, but it doesn't exist. So that means Rx alpha 1 on this W1, R meaning this, now the fundamental, is 0. In the state W1, let me just call it like this, W1. This is the eigenstate with the weight W1. So that's 0. So this is the highest weight with respect to that SU2. Now let's look at this SU2, Rx alpha 2, acting on the same state. Well, I should add, I have to add this vector. The result of this action, Rx alpha 2, acting on this, will be that I'll get some state which has the weight vector somewhere there. Add these 2 vectors, you get somewhere there, right? But that doesn't exist in this representation. So this is also 0. So you see what we are saying is that this particular state is the highest weight with respect to both of these SU2 subalgebras. This one and that one. Simultaneously, this is the highest weight. Now, this annihilates it both ways. Rx alpha 2 and X minus alpha 2 both annihilate it because there is no weight vector. So this is spin 0 with respect to spin 0 representation with respect to this SU2. Right? It doesn't do anything. But with respect to this SU2, this is the highest weight, and spin the J3 quantum number is 1/2. Again, dividing by 2. You have to divide by 2. Right? So this is spin half representation. So when I apply x minus alpha 1, I will just go here. Indeed, you can explicitly check that. I mean, this is 2 units, right? Here is 1 unit, there's -1. So when I apply it, will come. Right? So this is a doublet of this SU2. But then once I come here, this is no longer a singlet of that SU2. Because if you look at, if you actually project it here, this is 1 unit. Okay. So once again, this guy will become a doublet with respect to that SU2. Okay. And so when I apply x minus alpha 2, I'll come here. This is W3. And it stops there. And this guy, this also is a doublet, but it's a doublet with respect to alpha 3, this SU2. So there is this nice, I mean, you know, there's a very strong, you see, to appreciate how strict this condition is, that these guys have to be SU2 representation with respect to all the SU2s. This is very non-trivial, right? I mean, you cannot just choose anything. It is very, you know. And of course, all the representation is obtained once you specify your highest weight. Right? Because here the highest weight was, so we chose this to be with respect to these 2 SU2s. The SU2 with respect to alpha 1 root, and the SU2 with respect to alpha 2 root. Right? Let me write in terms of Lie algebra. Okay. So the SU2 Lie algebra, alpha 1, alpha 2. This W1, as we saw, both Rx alpha 1 and Rx alpha 2 annihilates it. And we are declaring these guys to be the simple roots, or positive roots, or raising operators. So this is the highest weight state. And once you specify your highest weight, then everything else can be obtained just by applying the lowering operators in a consistent way. Yeah? So the only thing that you have to specify is what, just like in SU2 case, you have to specify spin J, the value of J, and then the representation is fixed. J has to be, of course, integer or half integer. Now here again, once you specify this, so with respect to both R alpha 1 and alpha 2, it should have integer or half integer eigenvalues. Right? That is the important point. And once you have chosen any positive integer or half integer, non-negative integer or half integer values for these two, that fixes a representation. Irreducible representation. This is the main idea. Okay, so this was the, was there anything else I have to say here? Yeah. Now let's go back to the, I mean this was a nice symmetric thing. There were all the nice symmetries. For every alpha you had a minus alpha. So like reflection symmetries are everywhere there, right? I mean parity symmetries are there. But this diagram doesn't have, you see, for W I don't have a minus W, W1, W3 also. But there is another representation, which is what is called the complex conjugate representation. You remember the complex conjugate representation, RH goes to minus RH star, right, bar. But RH is real. I mean, I've chosen the basis. The bases are all real. So RH bar is the same as RH. H being the Cartan algebra elements, right? So minus is simply taking the eigenvalues and making them minus. Okay. Which means W1 will go over to minus W1. So this will be minus W1. So I will draw here. So something like minus W1. Here minus W2 will go to W2 will go to minus W2, and W3 will go to minus W3. So it will again be another equilateral triangle, but inverted. I mean, this one was this triangle, and that's the inverted triangle. And that will be the that will be the what we call, so it's denoted. So this one is, say choose some convention, say this is denoted as 3-dimensional representation. then the complex conjugate representation is denoted by 3 bar. To remember that it's a complex conjugate representation.
We can say that the 3 1 for quarks.
Quarks and anti-quarks, precisely. So this will be the, say quarks are transforming under this, the anti-quarks are transforming under that. That is how it works. Is that point clear? Maybe these pictures are all becoming too untidy because I'm drawing on top of each other. So, but I hope the meaning is clear, right?
How about gluons? What is the representation for them?
They are the adjoint representation.
Also.
Then the adjoint. So quarks and anti-quarks are in the 3 and 3 bar representation.
Yeah.
And the gluons are in that representation, adjoint representation.
Okay, so it's 8.
8, yeah, 8 dimensional. Okay, we will discuss also that. I mean, the gauge group always has to be in the adjoint representation.
Maybe it doesn't matter right now, but if we have the superpartner, singularity representation will be gluinos.
Gluinos will also be in the adjoint representation.
Okay.
So the point is that supersymmetry transformations commute.
Yeah.
These are some internal symmetries. No?
Yes.
So supersymmetry transformations will commute with their direct product groups, or at the level of algebra, they are direct sums. So they commute with all this. These are internal symmetries that we are thinking about. Whereas supersymmetry is a bit more complicated. It connects to the space-time symmetries. When you apply 2 supersymmetries, it gives you a translational generator. So it's kind of intertwines with the space-time symmetries. So that's more complicated. I mean, supersymmetry is and it's also graded algebras. Some of the commutators are replaced by anti-commutators and so on.
It's no longer SU3 in that case. It's
Also graded Poincare.
A graded Poincare, yeah, exactly. So it becomes more complicated. I don't know. I mean, in the previous years we used to have. Traditionally we used to have. That your courses are like 2 semesters, right?
Yeah.
So some of these courses they are exams. I mean, these are regular courses, what we call it, and we expect every student to have understood completely these subjects. The ones where there will be exams. But then on top of it, after all the exams are over in the second semester, there are some special courses are given where there is no exam.
Yes.
But it's and these are like crash courses. I mean, so very quick. Just to give you an idea. We don't expect you to understand everything in those extra courses, crash courses, but to get some flavor, some idea of what's happening. Which helps sometimes in the project, because you have to also do a diploma project, right? So, for example, many times people used to do a lot in string theory or something like that, no? And for that, it will be nice to know some supersymmetry. Or, for example, some people would like to go towards granularification theories, in particular supersymmetric granularified theories. So again, for that, it's good to know some supersymmetry. So we used to give a crash course on supersymmetry, but I think last year there was no supersymmetry course. I think. Okay, but instead of that, there were other subjects. There were
Mathematics and quantum gravity.
Quantum gravity was it? Oh, quantum gravity. Okay. Wow, that's difficult. Yeah. Okay. So I still have a few minutes. Now. Okay. So far, so can I erase this? No, that picture I don't want to erase because. Now let's talk a little bit about the tensor product of these representations. So we have the 3 representation and 3 bar representation, 3 and 3 bar representation, and of course the adjoint representation. These things we reasonably well understand in terms of eigenvalues, weights and roots. We understand that. No? Incidentally, you should check this. Here I mentioned that if I apply x minus alpha 1, you should get that. No? But since we have expressions for SU3, we can explicitly check it. No? We have the 3 by 3 matrix for the alpha 1, x alpha 1. If you apply that on W1, I mean this eigenvector, you should get that, and so on. Just check it for. So now if I take this, suppose I want to look at 3 times 3, tensor product. So tensor product, so remember how it works. So the tensor product, if I apply now R, the tensor product representation. So what's the dimension of this? This is 3-dimensional, that is 3-dimensional. So this is altogether 9-dimensional, 3 times 3. Tensor product is you multiply the 2 dimensions. No? So it's a total dimension of this space is 9. Is 3 times 3, which is 9. And the way RT of any element X, Lie algebra element X, doesn't matter, Karta or non-Karta, whatever, any X acting on this tensor product representation will be a sum of 2 terms. One is RT, R fundamental, let me put here fundamental, to remember this fundamental representation of X acting on the 3-dimensional representation, tensor product, the 3, plus, and then nothing happens to the first 3, and multiplying with the X acting on 3. I mean, in general, it was true. Let me call it some dimensional representation, N1 and N2 dimensional representation in general. So it will be N1, N2, N1, N2. And this will be the representation, the first representation, that will be the second representation. So that's a general structure.
It doesn't have to be the fundamental one.
Doesn't have to be fundamental, anything, yeah. So that's why I generalize it to, but we wanted to look at the details here for this general statement. Okay.
Can you find the SU3 representation of any dimension?
No. Irreducible representation.
Is there any upper bound on that dimension?
No, it can go all the way to infinity. I mean, as I said, so from this discussion you see, all you need to specify is the 2 numbers. So we have 2 SU2s. Let's say alpha 1 SU2 and alpha 2 SU2. So the alpha 1 SU2 was generated by this SU2, and alpha 2 was this. Huh?
But these are SU2 subalgebra. So
2 SU2 subalgebras.
We know that for SU2 there is a dimension of any
Exactly. True. So precisely. So what happens is that all you need to specify is the highest weight. And highest weight will be specified by giving 2 numbers, 2 non-negative numbers. The one is let's say this is the spin content, J1 and J2. J1 spin with respect to alpha, this is SU2 subalgebra, and J2 with respect to the SU2 subalgebra.
The dimension of
the dimension will be a more complicated function of J1 and J2. It's more complicated. No, there is a formula. I just don't remember the formula. But it is not simply 2J1 plus 1, 2J2 plus 1. I mean, it won't be simply 2J1 plus 1 times 2J2 plus 1.
Because it's not simple.
It's not. I mean, they have direct sum of this. I mean, the 2 SU2s are kind of more complicated. See, they don't commute with each other precisely. No?
It's not a simple algebra.
Yeah. I mean, it's not a direct sum. These 2 SU2 subalgebras, these are not direct sum. I mean, the SU3 is not direct sum of 2 SU. This SU3 algebra is not the direct sum of 2 SU2. That's because we see that this with commutation of this with that gives you that. No, it's not 0. So it's much more complicated. The construction is more complicated. I mean, maybe tomorrow I'll give some examples of this,
Okay.
perhaps.
So tomorrow please tell me the formula that you're talking about.
One of the?
The formula for the dimension.
There is a formula for that. I just don't remember now. Maybe it is given in the notes somewhere. Huh?
You can tell it to me tomorrow.
Yeah.
Okay.
Yeah. So, it's. I think. Okay. I mean, I can kind of make a guess, but okay. But we can check. But see. So, for example, I mean, if I had looked at this here, here you see you would have already gotten a wrong result, right? Because here, you see J1, for this representation, we said that this was a singlet under the other SU2, right? But this is a doublet under this SU2. So you would have J1 equal to half and J2 equal to 0, right? But then this formula would give you just 2 here and 1 there. That is not correct, right? You can use 3-dimensional representation. The reason is because you see, the moment I applied, you see, this was a singlet under that, right? But the moment I applied x minus alpha 1, I got there, this is no longer a singlet of that. Yeah. If it was a direct sum, it would still be singlet. No? So it's a non-trivial kind of embedding of these two SU2s, which is what makes it more non-trivial. So with this, what does it mean? As we saw from here, that if I now look at specialized to the alpha, the Cartan subalgebra, so this will be H and this will be H, right? And suppose I have chosen a basis, these are all eigenfunctions of the the H, then this will be the eigenvalue for this state, that will be the eigenvalue for that state, so eigenvalues add up, which means the weights add up, right? So therefore, now if I look at this diagram, so let's focus on, so again, this is too many lines here. So, okay, yeah, let's do it here. But sorry, this is unreadable, right? Okay, so I do it here. So here is the unit 1, and this is supposed to be 30 degrees. 30 degrees. So this is W1, and then here was W2. I mean the exact opposite of this. Something like this here. So here W2, and W3 was twice this length here, so somewhere here. W2. Okay. And now I'm taking 3 times 3. So what are the weights of this? I just have to start adding. So there are 9 states. So 3 times 3. I just add pairwise the same weights because it happened to be the same. 3. If I had taken 3 with 3 bar, it would not be the same. But let's first take 3 times 3. Then we can go to 3 times 3 bar. So now I just add pairwise. Pairwise. So first of all, I can have W1 plus W1, right? I can take the W1 eigenstate here and W1 eigenstate there. Then the result will be 2W1. So add that up. So one of them will be that. Maybe I should put a cross here to indicate that this is for the tensor product. So these are dots here, circles. Okay. Then you have similarly W2 plus W2. I can go there, it's a double, so it comes here, and similarly here, which goes out of the blackboard. So it is there, somewhere there. Okay. Then I can take the sum of these two, which will come here, somewhere here. Okay. Sum of these two, which will come, if I continue down there, it should come somewhere here. Okay. And then sum of these two, which will, if I continue this line here, no, this line, so it's something like this here. Okay. So we get 1, 2, 3, 4, 5, 6. What else are we missing? We are missing some things. What are we missing? What did I do? I took this with that, got this. This with that, I got this. Now this with that, I got this. What am I missing? Doubling, right?
You need the double.
Double. So how will I get it? Ah, sure, of course, yeah. So you can take W1, W2, W2, or you can take W2, W1. Correct? I mean, from this guy I take the weight W1, from here I take W2, or vice versa. So the multiplicity. So each of them are coming with the multiplicity 2. Okay. And this one. Whereas this is coming with only one multiplicity. Okay. Now look at this state. I mean, with respect to alpha 1 and alpha 2, SU2 subalgebras, this is the highest weight state. Because if I apply x alpha 1, which is alpha 1 is this one, in this direction, it will move you this way, but there is no other weight here, right? So this is clearly the highest weight. And the same thing, if I apply alpha 2, which is somewhere here, it will push you up there, and there is no such thing. Okay? So this is the highest weight state of the both SU2 algebras. Okay? So certainly one representation will be in the language of the J1, J2. One of them will be 1, 0, right? Because no, not yet. I mean, I have not concluded that. This is the highest weight, but you see, its eigenvalue here with respect to what is it? Alpha 1 thing. This was 1, so this will be 2, right? But the 2, because we have to divide by 2, so it is spin 1. J equal to 1. So it is spin 1. And then from here, as we saw, this was already, it had 0 component along the alpha 2 direction. And this is simply continuation of that. So this will be also 0. So spin 0. You can check that. It's 30 degrees here, right? And that was 120 degrees. So this angle is 90 degrees. So it's orthogonal. So that's spin. So now what I do is I can start applying. So certainly I know there is this representation. Like what we did for spin SU2 case. I take J1, J2. So the highest weight will be J1 plus J2. Then I take that reducible representation, remove it, and then ask the question, what is the next highest weight state, right? The same procedure here. So I do this, and you can see that when I apply, so I want to start applying lowering operator. Okay. So I apply x minus alpha 1 here, and x minus alpha 1 here. I come there. This had to be because it's spin 1, so there should be 3 in the SU2 subalgebra of that, right? In that representation. So these 3 come here, but only one of these states. Here there are 2 states, but only one state. Okay. And then, okay, you can again start from here. So you have got one state here, and then apply the lowering operator of alpha 2. So I will get that one state here. So you remember, out of this 2, it splits into 1 plus 1. One of them comes when you apply lowering operator. So let's say this one. So here I have only one state, right? I apply x minus alpha 1 on this state. So I'm going to get some definite state, one state. So that's suppose that state. There is still something remaining there.
But that's the other highest weight.
That will be another highest weight state, right? So you take this, then you apply again another x minus alpha 1. I will get that state. There is only one state here, which is okay. Now take this state here and apply x minus alpha 2. So x minus alpha 2 is going backwards this way, right? So you go backwards this way, and I have not drawn it very precisely, but you should end up there. Okay. But since I am applying on this state, this splits into 1 plus 1, but x minus alpha 2 takes this state to say one of this state. Okay. So this way you can see that in this representation, similarly you can go from here, from this is only one state, and I apply x minus alpha 2. So I'm going to get this state. There will be one state. So in this representation, starting from here as the highest weight, you're going to get only 6 states. The 3 of these extremum states, and 1 each from this point. Okay. So this 3 times 3 splits into a 6-dimensional representation. Then I'm still left with the 3. But what are those 3? They are, so the remaining one each from here, but the weights are these 3. But this is exactly what we call 3 bar. Right? This was just a reflection of, you can verify that it is just 3 bar. So that's how it's splitting. On the other hand, if you had taken 3 with 3 bar, so suppose I had taken 3 with 3 bar, then the weights will be, so okay, now I can I erase this, and work on this. So here, so here was my 3, right? And then the 3 bar is this, so let's say here, I don't know, cross, let's say, 3 bar I put here. So it's here and here. And now, so this is the weights of the 3 representation, and these are the weights of 3 bar. tensor product of 3 with 3 bar will be again, just start adding up all the weights. You'll get the tensor product weights. So when I add these two, I'm going to get so this was 30 degrees, so this is going to be completely 60 degrees, right? So you go here, somewhere here, and you see this projection will be the same, right? Because this has no zero component along the x direction, so it will be somewhere here. Maybe a picture something like this here. And this with that will give me this with that will give me a line here, because both are 30 degrees, equal length, so it will be along that. This with that will give you here, and this with that will give you there, and this with that will give you here. Okay. So you see, you exactly, and you can just add up all these the precise numbers, you will reproduce these non-zero roots. Okay. So these are all coming with multiplicity 1, 1, 1. These are all coming with 1, 1, 1. Okay, because the only way to get here is to take, so I'm taking a 3 with 3 bar, right? So the weight W1 and say plus W1 bar. That's only one way of doing it. But then what about here? You see, I can take this with that gives you 0 weight, this with that gives you 0 weight, and this with that gives you 0 weight. Okay. So what we are seeing is that you reproduce when the sums reproduce alpha 1, alpha 2, alpha 3, plus minus, plus minus, plus minus, with each with multiplicity 1. And 0 weight with multiplicity 3. No? Because there are 3 ways of getting to 0. You have a W1 and then minus W1, which is the anti-fundamental, right? 3 bar. W2 minus W2 and W3 minus W3. You add that up. So there are 3 ways of getting this. That's how it splits, right? So 9, total number of states must be 9 here. 3 with 3 bar. So 3 with 3 bar. Total must be the 9, out of which 6 of them are this and 3. 6 because no, 8, sorry, 8 of them, because plus minus sign, plus minus sign, plus minus sign, 8 of them here. No, sorry, what am I saying? No. No, 6 of these states. So there are 6 of these states and 3 of these states. So 9 altogether. Now, if you look at here, I mean, these weights are exactly the roots of the adjoint representation. So you're going to get certainly an adjoint representation. So 3 with 3 bar will certainly contain an 8, but this 8 has these non-zero roots plus 2 of the 0 roots, because Cartan subalgebra is 2-dimensional. Those are 0 eigenvalues, right? But then I have 1 left, which is 0. Once I have removed these 8 states, then what will be left over will be highest weight state again, right? That highest weight is 0, 0 spin. J1 and J2 both have 0. So that will be a singlet. So that's how it splits.
Physically we can say that the tensor product of 3 and 3 bar is actually the particle that we can make from one quark in another quark.
Correct.
And we have 8 mesons of one type and 1 meson of the other type.
Yeah. You can do that. Yeah, QQ bar. QQ bar will have a octet and a singlet. Yeah. Right. I mean, when you construct the action, suppose I want to even write down a kinetic term for the quarks. Quarks are fermions, so it will be something like Q bar D slash. You have done gamma mu d mu, and then Q. No. Now, as far as the group internal symmetry is concerned, which are SU3 triplets both, Q and Q bar, you pick out the singlet part of it because you want SU3 invariant to construct the action. But of course, QQ bar, the composite like mesons, they can also be octets. So. But of course, I mean, here it is not, because when we talk about SU3, this is the color quantum number, no? And SU3 is confined, which means every physical state that we find should be SU3 singlet. Okay, it's completely confined. It's so strongly interacting, it's confined. You cannot separate out a quark. So therefore, in all the mesons, etc., this SU3 will be always a singlet. Because this is a color SU3. Then of course you can talk about flavor symmetries. The flavor symmetries is different. Color symmetry will be always singlet. Okay, so I think tomorrow we'll continue with this SU3 representations a bit more. So far, you see what we have seen is that in this representation there were only one state for each of them. No? But that is not the case. Like in SU2 it happens, right? For every m quantum number, Jm, right? Every m quantum number multiplicity was 1. There was only one state in the irreducible representation. That is not true in SU3 case. We will see that. Okay. I'll close this.